When we talk about the sheer incomprehensible scale of the universe, we usually point our telescopes up, right? We talk about billions of galaxies, trillions of stars.
Right.
But today, I want to give you a number that plays in the exact opposite direction, all the way down to the microscopic building blocks of everything. And that number is 10 to the power of 60.
Which is, that is a 1 followed by 60 zeros.
Yeah.
It's a number so impossibly large and effectively breaks the human brain's ability to even visualize it.
And what's wild is that this isn't like the number of atoms in the galaxy. That is the estimated number of potential molecular configurations that actually exist in drug-like chemical space.
Staggering.
Just to put that into perspective for you, if human experts set up a traditional lab, tried to physically synthesize and validate all of those potential molecules, the universe would burn out and end before they finished even a fraction of a percent.
Oh, easily.
Yeah. And that impossible math is exactly what we're tackling today in this deep dive. We're looking at some incredible insights from a 2026 paper published in Nature by researchers Kwok, Chowdhury, Yoon, and Keen.
Right. The paper titled Efficient and Valid Large Molecule Generation via Self-Supervised Generative Models.
Exactly. And our mission today is to understand how AI is finally stepping up to design these massive, wildly complex molecules that could actually cure diseases like cancer.
Which is arguably one of the most critical frontiers in modern drug discovery. We've spent the last decade watching AI get very, very good at inventing simple, small molecule drugs.
Like aspirin or ibuprofen.
Yeah, exactly. But the medical field desperately needs what we call large molecules for cutting-edge gene therapies and, targeted immunotherapies. And crossing that bridge from small to large has just been a complete computational nightmare.
Okay, let's unpack this. If large molecules are just larger. My instinct is to just take the AI models that are already really good at inventing small molecules, give them more computing power, and tell them to build bigger things. Why doesn't that work?
Well, because the physics, and specifically the physical chemistry, completely change as the scale changes.
Really?
Yeah. Large molecules aren't just like scaled up, stretched out versions of small ones. They are an entirely different beast.
Right.
So imagine a small molecule, like a rigid, simple Lego block. It's stable. Its shape is totally predictable.
Okay.
Now, imagine a large molecule like a long strand of cooked spaghetti that is heavily coated in Velcro.
Oh, wow. So they're incredibly floppy and they stick to everything.
That is the perfect way to visualize it. In chemistry terms, we say they have a high degree of conformational flexibility.
Meaning they bend and twist a lot.
Exactly. They constantly twist, fold, and bend into countless different 3D shapes. And on top of that, they possess multiple reactive functional groups.
Which are what exactly?
They're basically highly specific clusters of atoms that are just eager to chemically react with anything they bump into.
Ah, the Velcro.
Right, the Velcro. This makes them incredibly difficult to stabilize and synthesize in the real world. So it's not just a puzzle for a computer, it's a fundamental puzzle of physics. The AI models that conquered those small data sets just absolutely shatter when faced with this level of structural nuance.
Which brings us to the first major roadblock I noticed in this research, which is the data format itself. How do we actually describe a floppy, highly reactive Velcro spaghetti molecule to an AI in the first place?
Right. Well, traditionally, the gold standard in computational chemistry has been to use two-dimensional or three-dimensional graphs.
Like those ball and stick models from high school chemistry?
Yeah, or a classic network diagram. The atoms are the nodes, and the chemical bonds connecting them are the edges.
Got it. And the paper mentions the Moses dataset, right? Which is like the benchmark for small molecules. The average weight of a molecule in that dataset is about 307 Daltons.
Right, a Dalton being a standard unit of molecular mass. So at 307 Daltons, you're looking at maybe 20 to 25 atoms.
Okay.
And for a data set like Moses, graph-based AI models like JTVAE or graph neural networks, they work brilliantly. They can map out those 25 atoms and their bonds without breaking a sweat.
But then the researchers looked at the Chembl Large Dataset.
Yes.
Which is a collection of bioactive, drug-like large molecules. And the average weight there is 1799 Daltons.
Yeah, so now you're dealing with well over 100 atoms per molecule.
And I'm assuming that when you feed a massive 100-atom 3D graph into the AI, it doesn't go well.
The models literally crash. Up to the point of this research, there were practically no reported graph-based generative models successfully trained on molecules with more than 100 atoms.
Wait, I'm hung up on the 3D thing, though. Throwing away a 3D structural map sounds like a terrible idea for something that exists in the physical world.
It does seem counterintuitive.
It feels like you're trying to describe the intricate blueprints of a 100-story skyscraper using only, like, a single long run-on sentence.
Right.
Why can't the computer just handle a bigger shape?
I agree. It sounds like a bad idea to throw away dimensional data. But the researchers were forced into this compromise by a mathematical wall called quadratic memory scaling.
Okay, unpack that for me. What is quadratic scaling actually doing inside the computer?
Well, think about the relationships between things. If you have a small social network of 10 people and you want to map out every single possible relationship between them, the computer has to calculate 100 potential connections.
10 squared. Okay, that's easy.
Right. But if you have 100 people, the possible connections aren't just 10 times harder to calculate. It's 100 squared.
Which is 10,000 connections.
Exactly. So when a graph neural network tries to analyze a large molecule, it has to compute the spatial relationships and bonds between every single atom and every other atom simultaneously to understand the whole structure.
So the computational cost doesn't just climb a ladder, it launches like a rocket.
Yeah.
The memory requirement skyrockets until the RAM just gives up.
Exactly. The system exhausts its memory before the AI can even finish a single training run. So if 2D and 3D graphs mathematically crash our systems, we must reduce the dimensionality.
Okay.
The researchers had to flatten these massive molecules into 1D strings of text. They basically had to turn structural chemistry into a written language.
Okay, let's do a quick recap here. Large molecules basically break 3D graph AI models because computing the connections just drains all the memory. So the solution is translating chemistry into 1D text. Which brings me to a question for you listening. Think about your own work for a second. When was a time you had to drastically simplify the format of your data just to get a software program or even just a coworker to process it? Because that's exactly what's happening here.
It's a universal problem, really.
Yeah.
Yeah.
But if we are flattening chemistry into text, I mean, you can't just type "make me a cancer drug" into a prompt, right? What language does the AI actually speak?
Well, in the paper, they focus their testing on the two main 1D chemical languages, which are SMILES and SELFIES.
Right, SMILES,
Yeah.
which stands for Simplified Molecular Input Line Entry System. The paper notes this has been the industry standard for decades. It's relatively compact, and human chemists can actually read it and write it.
Yeah, they can.
But you mentioned earlier that the AI models shatter when dealing with nuance, and the paper calls SMILES incredibly brittle. Wait. If human chemists can read it just fine, why is an advanced AI suddenly tripping over its own shoelaces when trying to use it?
Because human chemists have intuition, right? And AI relies purely on syntax.
Oh, okay.
Think of SMILES like old school computer code. It relies heavily on strict, rigid syntax rules. So you have to match opening and closing brackets to show a branch in the molecule, and you have to use specific paired numbers to show closed chemical rings.
That's very unforgiving.
Extremely. When a generative AI is hallucinating or inventing a new molecule from scratch, it's essentially just guessing the next character. So if it makes a single typo, say, it opens a bracket for a chemical branch but forgets to close it 40 characters later, the entire string becomes chemically impossible.
It's basically a syntax error.
Yeah.
And the software they use to parse these strings, RDKit, just looks in and says, this isn't a molecule, this is garbage.
It rejects it completely, which is a huge waste of computational time and energy. SELFIES, on the other hand, which stands for self-referencing embedded strings, was designed specifically to fix this brittleness.
Oh, so?
It completely abandons that rigid bracket syntax for a mathematically robust grammar system.
Wait, how does a grammar system guarantee structural validity?
It's essentially a closed mathematical loop. With SELFIES, the state of the molecule is continuously derived from the previous characters. It's like snapping together magnetic train cars.
Oh, I like that analogy.
Yeah, you can connect them in a completely random order, and you might end up with a very, very weird-looking train. But because of how the magnets are designed, it will always be a functioning train. It will never be just a disconnected pile of plastic. It is virtually impossible for an AI to output a SELFIE string that doesn't at least represent a theoretically valid physical molecule.
And the data from the paper backs this up dramatically. They tested recurrent neural networks, which are specifically built to predict text sequences, using both of these chemical languages.
Let's hear the number.
In the SMRNN model, which uses SMILES, the validity of the generated molecules on the Chumbo large dataset was about 89%. Which, sounds okay until you look at the SFRNN model using SELFIES.
Right.
The validity jumped to nearly 99%.
Which proves a massive lesson for anyone working in machine learning, really.
Yeah.
How you represent your data to the machine is often just as important, if not more so, than the complexity of the algorithm analyzing it.
Yeah, absolutely.
By giving the AI a structural safety net like an aggressive autocorrect that guarantees every word is at least in the dictionary, they removed a massive layer of failure.
Okay, mini recap time. SMILES is a brittle language where one mistake ruins everything. SELFIES acts like a structural safety net, ensuring every generated molecule could theoretically exist. So question for you listening. Imagine typing a long email where one typo deletes the whole message, that's SMILES, versus an aggressive autocorrect that always makes a real word, that's SELFIES. Which would you trust an AI to use?
I think the answer is pretty obvious there.
Exactly. Okay, so we have a language that won't break. Here's where it gets really interesting, though. You still have to teach the AI the underlying rules of that language.
Right. The physics.
Yeah, you don't want it to just memorize the data set and spit back existing molecules. You want it to actually invent new ones based on the laws of chemistry. How do they teach it physics and chemistry using just text?
Well, they don't explicitly program those rules. That would be impossible. Instead, they force the AI to discover them through a technique called self-supervised learning.
Okay.
And specifically, they used a mechanism called self-supervised masking.
I read this part of the methodology, and I instantly thought of a game of Mad Libs, or like taking a fill-in-the-blank test in grade school.
That's a highly accurate analogy, actually. During the training phase, the researchers took these 1D molecular strings and intentionally masked, or hid, a random portion of the characters.
Like how much?
Usually between 5% and 20%. They just replaced them with a blank mask token. Then they fed that incomplete string into an LSTM.
An LSTM being a long short-term memory network.
Right, which is a specific type of neural network that's just excellent at handling long-range dependencies and sequences. The researchers forced the LSTM to predict what those missing pieces were supposed to be based entirely on the surrounding context.
Which means the model can't just memorize the training data, because the data keeps changing, right?
Exactly.
It has to look at the atoms on the left, look at the atoms on the right, and actually figure out the latent structural patterns, like the hidden rules of how atoms actually bond to guess the missing piece. It's like when you're trying to learn a complex new topic. You always learn better by testing yourself with flashcards that intentionally have missing information rather than just passively reading a textbook.
Yeah, that active retrieval builds a much deeper model of understanding. But there is a massive catch here that the researchers had to navigate, which is the trade-off between novelty and validity.
Okay, what do you mean?
Well, if you want the AI to be highly creative, to generate highly novel molecules that have literally never been seen before in human history, you have to increase the masking percentage.
You hide more of the answer, so the AI has to guess more wildly.
Precisely. But when they increased the masking to 20% on the models using the SMILES language, things just fell apart. The AI definitely got very creative, but its validity absolutely plummeted.
Because it didn't have enough context.
Right. Without enough context, the AI couldn't figure out where to put those strict syntax brackets we talked about, and it just started generating a ton of chemically impossible junk.
Ah, but look at what happened when they used selfies. Because selfies has that built-in structural grammar, those magnetic train cars, the validity stayed incredibly high.
It did.
The researchers even pushed the masking to an extreme 90% in preliminary tests. Imagine handing someone a book where 90% of the words are blacked out and asking them to write the rest of the story.
It's crazy.
With SMILES, it crashed. With selfies, the validity barely dropped at all. It perfectly navigated that trade-off, allowing the AI to be highly novel and creative without breaking the laws of physics.
Which is a huge victory. But, even with selfies guaranteeing validity and the masking driving the novelty, they ran headfirst into another major roadblock. And this one is specifically tied to large molecules sequence length.
Okay, quick recap and question before we dive into sequence length. Basically, hiding parts of the data forces the AI to learn the deeper rules of chemistry. Masking increases creativity, which is novelty, but risks errors, which is validity. A trade-off selfies perfectly navigates. So for you listening, when you are learning a complex new topic, do you learn better by reading a complete textbook or by testing yourself with flashcards that have missing info? It's the exact same principle.
Yeah, it really is.
Okay, so back to the roadblock. sequence length.
Yeah.
Right? Because we flattened a giant 3D structure into a 1D string. That string is naturally going to be incredibly long.
And it is. A large molecule from that Chembl dataset averages about 122 tokens or characters in length.
Okay.
Now, 122 characters might not sound like much to you and me. I mean, it's shorter than an old tweet. But in the AI world, particularly for advanced transformer architectures, it creates a massive bottleneck.
I see the word transformer thrown around constantly with AI, but in this specific context of parsing a long string, what is the transformer actually struggling with?
So transformers rely on something called self-attention mechanisms. Think of self-attention like trying to read a very complex mystery novel.
Okay.
To understand the plot twist on page 100, the AI has to simultaneously keep its finger on a clue from page 5, a conversation on page 50, and a detail on page 99. It has to pay attention to every single token in the sequence in relation to every other token to understand the full context.
Oh, wow. So we're right back to that quadratic scaling problem, just in a different format.
Exactly. Instead of mapping 3D spatial nodes, the computer is mapping text tokens. The memory and computation required scale quadratically with sequence length.
Right.
So at 122 tokens, the self-attention mechanism requires so many cross-comparisons that it bogs down the most advanced models. The training just becomes hopelessly slow and, frankly, computationally expensive.
So how did they shrink the sequence without losing the actual chemical information?
They introduced a compression hack borrowed straight from natural language processing. It's called Atom-Pair Encoding, or APE. Yeah, and it is very similar to the byte pair encoding used to train models like ChatGPT.
So what is APE actually doing to the chemistry?
It's purely statistical. The APE algorithm scans the entire data set of molecules and looks for the most frequently co-occurring adjacent tokens.
Meaning things that show up next to each other a lot.
Right. When it finds a pair of atoms or structures that almost always sit next to each other, it statistically merges them into a single brand new token.
It's funny, the AI is essentially doing exactly what we do with our emails and text messages to save mental bandwidth.
How so?
Like instead of writing out be right back, which is 3 separate words, or tokens, you just type BRB.
Yes.
It's one token. It means the exact same thing. No data is lost, but it's 3 times shorter.
That's a perfect analogy, and the impact of this on the AI models was staggering. APE compressed the average molecular sequence length of these giant CHEM molecules from 122 tokens down to about 50 tokens.
That is a massive reduction in the computational load.
And because it operates as a lossless compression mechanism at the string level, meaning every BRB can be perfectly unpacked back into be right back, it slashed memory usage without losing a single drop of chemical realism.
Wow.
This allowed the researchers to finally train those powerful, attention-based transformers on large molecules efficiently. But honestly, here's the best part. It didn't just make the AI faster, it actually improved its generative performance.
Wait, how does compressing the text make the AI better at inventing drugs?
Because the AI isn't wasting its attention budget on trivial repeating atom pairs, it can focus on the macro structure.
Yeah.
The models using APE consistently achieved higher novelty and internal diversity.
And internal diversity, or indiv, being a crucial metric, because you don't want the AI to just generate the exact same narrow template of a molecule 10,000 times. You want a wide variety of candidates.
Exactly. So by compressing the data, they freed up the transformer to actually be more creative.
That's brilliant. Okay, recap time. APE shrinks long chemical strings by combining common atom pairs into single symbols, speeding up the AI without losing any chemical realism. So, question for the audience. How many APE-style mental shortcuts or acronyms do you use in your daily life to compress complex ideas into single words? It really is just an efficiency hack.
Oh, we all use them constantly.
Yeah, we do. Okay, so what does this all mean? If I'm understanding this incredible stack of technologies, we now have a highly efficient AI running on transformers using APE compression, speaking a guaranteed valid chemical language in selfies, and forced to learn deep chemical rules through self-supervised masking.
That's the stack, yeah.
And it can rapidly invent highly novel, complex, large molecules. But, and this is a big bet, if we're trying to cure a specific disease, say a tumor in the liver, we don't just want a bucket of random large molecules, right? We need to design them for highly specific biological tasks. How do we steer the wheel of this AI?
That is the ultimate goal, conditional generation. To test if they could actually steer the AI, the researchers created a mixed data set.
Okay, what's in it?
They took all the small molecules from the Moses dataset and dumped them into the exact same training pool as the massive molecules from the SMILES dataset.
Which seems like it would create a huge psychological challenge for the AI, honestly.
Yeah.
Because small molecules are fundamentally simpler to map and generate, my guess is the AI will naturally just default to generating small molecules.
Which is exactly what happens. Algorithms will basically always take the path of least resistance.
Right.
So to overcome this natural bias and force the AI to build what they actually wanted, they used a technique called prefix-based conditioning.
Which is essentially just slapping a label on the instructions before handing it to the AI.
Exactly. They analyzed the data set and discretized specific physical properties into statistical bins: low, medium, and high. For example, they looked at molecular weight. They also looked at log P.
Log P, which is a critical metric in pharmacology.
Very much so.
It measures lipophilicity, or essentially how fat-soluble versus water-soluble a molecule is, which matters tremendously because a drug has to be able to dissolve in your bloodstream, but also pass through the fatty membranes of your cells.
Right. So they calculated the weight in log P for every molecule, and then during training, they put a fixed order tag at the very beginning of the selfie sequence.
Okay.
They basically told the AI right up front, pay attention to this. The molecule you are about to study is heavy and it is highly fat-soluble. They forced the AI to associate that prefix tag with the structural patterns that followed.
So when they ran the model at inference time, like when they actually asked it to generate new drugs from scratch, did it listen to the tags?
It did. The prefix completely shifted the statistical distribution of the generated molecules.
Really?
Yeah. When they prompted the AI with a tag for high molecular weight, the output shifted systematically away from the small Moses molecules and heavily into the massive Chembl range.
Wow.
And when they tagged it for high log P, it generated highly lipophilic molecules. It proved definitively that we can actively steer this AI to design molecules with specific targeted physical traits.
Okay, final recap for this section. By adding simple prefix tags before the chemical sequence, scientists can successfully direct the AI to generate molecules with specific physical traits, like weight or solubility. So think about it. If you had a generative AI for your specific job, what prefix tags would you use to steer its daily output?
I could think of a few for my own work, for sure.
Right. It's incredible. By just adding a few contextual tags up front, you overcome the AI's natural laziness and force it to design exactly the type of tool the medical field needs.
And if we step back and look at the bigger picture here, what Kwok and the research team have achieved is a monumental proof of concept.
Yeah.
For years, the sheer size, the conformational flexibility, and that reactive chaos of large molecules made them a computational dead end.
The Velcro spaghetti.
Right, the Velcro spaghetti. But by accepting the friction of stepping away from 3D graphs, adopting the mathematical safety net of selfies, enforcing structural learning via masking, and compressing the whole thing with APE tokenization, we finally have a scalable, workable framework.
It is the toolkit that will be used to design complex biologics, peptides, and macrocycles. The exact things that represent the future of medicine. So the next time you are reading a news article about a breakthrough targeted cancer therapy or, a highly specific gene regulator, I want you to remember this. The sheer math of finding that one specific molecule out of 10 to the 60 possibilities was once deemed impossible.
Truly impossible.
But it was solved by taking the infinite complexity of physical chemistry, flattening it into a language, and teaching an AI to play a highly compressed game of fill in the blank.
And that actually leaves us with one final, deeply provocative thought.
Oh, what's that?
I want you to think about that APE tokenization process one more time, the compression hack. The APE algorithm does not know any chemistry. It is completely ignorant of physics, of covalent bonds, or electron sharing. It just blindly squishes frequent text characters together based entirely on statistics. It is just an aggressive autocorrect looking for patterns.
It's purely math. It doesn't know what a carbon atom is.
Exactly. Yet doing that purely statistical compression perfectly preserves chemical realism, maintains structural integrity, and actually improves an AI's ability to invent viable drugs.
That's wild.
It is. So the puzzle I leave you to ponder is this. Does an AI actually need to understand the physical laws of chemistry to design a life-saving drug? Or is the seemingly infinite reactive chemical complexity of our universe at its core just a vast statistical pattern waiting to be decoded by a really good autocorrect?